not going to be here ahead of time because, I mean, like, I'll see, obviously, if you're not here. But for you guys, if you could, like, if somebody isn't here, and you're like, hey, you should record the lesson. That's really helpful. And then I can send it to them later. Or if you're out, I can send it to you later. Okay, so we got rid of that extra minus here. Looking at this equation, you're like, what could we do? It's not a polynomial equation because those are rational exponents, right? Like fractional exponents. But looking at this, we could kind of like use strategies that we're familiar with from solving quadratic equations. Like looking at each of those terms, it's maybe a good idea to always first check and see, is there a greatest common factor that we could factor out? And in this case, the answer is yes. So if we thought about factoring out the GCF, which would be x to the 1/3 power, and then we're thinking about, you can think about, remember, dividing each of these terms, or thinking, okay, well, what times x to the 1/3 would give me x to the 7/3, and the answer would be x to the 6/3. But x to the 6/3 can also just be written as x squared. And then if we think about dividing the 3x to the 4/3, right, by x to the 1/3, or you could think about what times x to the 1/3 would give you the 3x to the 4/3, right? It would be 3x to the 3/3, right? 1/3 plus 3/3 would give you 4/3. When you're multiplying and you have the same base, you add the exponents, which can just be written as minus 3x to the first power minus 4. And then from there, you're like, oh, this is familiar. Does that quadratic factor? To what? Cool, so then now we have a product equal to 0. We're allowed to think, hey, zero product property. So if you need to pass through the step of going, well, x to the 1/3 is equal to 0, or x plus 1 is equal to 0, or x minus 4 is equal to 0, in order for that to be a true statement, and then go x is equal to 0, x is equal to -1, or x is equal to 4. You could just go directly by inspection to 0, x equals to 0, -1, or 4. I would separate with commas or ors. Or if you want to use set notation to summarize your solution. Questions? This is familiar, yeah? All right, then let's talk absolute value equations, which is the last type of equation that we're going to look at in section 0.3. So, the definition of absolute value, or one of the definitions of absolute value of a real number A, is represented by the symbol with the like vertical bars and then A inside, is defined. Well, one definition would be that the absolute value of A is equal to itself if A is greater than or equal to 0, or is the opposite of A if A is less than 0. The absolute value of a real number also represents the number's distance from 0 on the real number line. Okay, so since the absolute value of a number represents a distance, it will always be positive, right? Distance is always positive. So when the absolute value is involved in algebraic equations, we interpret the definition as if absolute value of x is equal to a, then x is equal to negative a, or x is equal to positive a, where a is greater than or equal to 0. Meaning, if we have the absolute value of x plus 4 equals to 23, and we're trying to solve for x, that means that whatever is inside here could be equal to positive 23 or negative 23, where then when we take the absolute value, we would get an output of 23. So we can write this as x plus 4. We split this into two equations, right? Is equal to negative 23, or x plus 4 is equal to positive 23. Do we follow why that is? Right, because the absolute value of negative 23 would be equal to 23, or the absolute value of positive 23 would be equal to 23. And then we can just solve each of those equations. So we'll get x equals to negative 27, or x equals to 19. And you could do a mental check, right? Each of those values, if you substitute them back in, would give you the correct solution. But you're not going to run into an extraneous solution here. We didn't do any algebra that would potentially create solutions that don't actually make sense. Good. Great. Okay, little bit more complicated. We can treat the terms or the products that have absolute value of x minus 4 in them like terms. Meaning, let's try and get the absolute value of x minus 4 on one side of the equation and then a constant on the other, so then we can think about solving from there. Like we could think about adding 3 times the absolute value of x minus 4 to each side of this equation, which would just give us the absolute value of x minus 4. And then we could think about subtracting by 3 on each side, which 11 minus 3 is 8. So then to make this a true statement, either x minus 4 would be equal to negative 8, or x minus 4 is equal to positive 8. So x would be equal to negative 4, or x would be equal to positive 4. I am. Oh, did I make a, whoops, I did. I was just making sure you're paying attention. What should that one be? Oh, that wasn't your question.
Yeah,
Okay.
I'm kind of confused where the other x minus 4, because there's x minus 4 on both sides.
Oh, okay. So let's think about this. To make this a true statement, like if we, x minus 4 just represents a quantity, right? Like if we thought of that as being a, right? To make this a true statement, ignore the x minus 4 for now. To make this a true statement, couldn't a be equal to either negative 8 or to positive 8?
Yeah. Oh, wait.
And if,
I'm confused.
right, because absolute value, so if we had absolute value of a is equal to 8. That means that a is either equal to negative 8 or a is equal to positive 8 to make that true, right? But in this case, a is x minus 4.
Yeah.
So that means that x minus 4 is either equal to negative 8 or x minus 4 is equal to positive 8. Right? And then when we substitute those values that we end up with for x back in, well, you can substitute in here or here. So negative 4 minus negative 4 would be negative 8, right? So absolute value of negative 8 is 8. That's true. Left-hand side equals to the right-hand side. If we plug 12 in, 12 minus 4 is 8. Absolute The really tricky ones are the absolute value inequalities. We are not going to do those. We don't need to. Okay. Similar idea, a little bit different. Why don't you, how about you two, go ahead and try this one together. Here with my mouth.
Yeah.
Talk to each other. Make sure you have the same ideas.
Positive and negative too.
Nice. Such good teamwork. Teamwork makes the dream work. That was
Do we need another minute, you guys? Is that it? That's all I got on there. Questions? Do we get it? How many solutions did we get? 4.
Positive, negative.
Oh yeah, what's up?
Plus or minus 3 or plus or minus root 5. So it looks a little bit different, but same strategy. Okay, that's the end of 0.3. So you'll have some practice on 0.3. But we are going to go into section 0.4 and start reviewing inequalities. And while we're reviewing inequalities, we're also going to review interval notation.
Is it in school at you?
You have to go through the agenda.
Oh, did I forget to put it on learning resources? Drop the ball. It's really like hard. I need to start making like a checklist to go through every day because I'm having to update 3 different classes. And so like I dropped the ball on posting your homework and on linking that. But I need to start like having like a checklist like, oh, I've completed this class. Now I've completed this class. Now I've completed this class. So we've just talked about solving equations, right? And now we're going to talk about coming up with the solution sets for mathematical statements that are not equalities, but they are inequalities. So whenever you have like an expression is greater than another expression, or is less than or equal to another expression, and coming up with all of the values that would be part of the solution set, which is usually like there's infinitely many values that can be represented using different notation. So like you probably, in Algebra 1 would have started or been introduced with inequalities where you were solving linear inequalities. Like you first probably would have started with like thinking about statements like x is greater than 2. Like what values would that represent on the number line? And you did the thing where you would like put like either an open circle or parentheses on 2, right? And then you shade in the direction that represents the solution set. Like that would be like a really simple linear inequality, and then you probably would have stepped it up a notch and had to think about falling back on strategies that you had previously used to solve linear linear equations. So like thinking about adding a quantity to each side of the inequality, or multiplying or dividing or subtracting on each side of the inequality in order to get x by itself on one side of the inequality and a constant on the other to represent the solution set. And then from there you probably would have stepped it up a notch and done some compound inequalities. So inequalities that are connected with either and or, like where x is greater than 2 and less than or equal to 7. Or like x is less than 0 or x is greater than 10. So I want to get into the different notations first that can be used to represent a solution set. Really, I need you guys to be comfortable with the inequality notation and the interval notation. So like I think you're probably most comfortable at this point with the inequality notation, but being able to go from inequality notation to interval notation and being really solid with the interval notation and understanding what that means. And then we'll also get into like how those compound inequalities can be represented, and thinking about intersections of intervals or unions of intervals and what that means. Okay? So inequality notation is whenever you have a statement where you have two expressions that are connected with like less than or greater than or less than or equal to or greater than or equal to. So an example could be like x is less than or equal to 2, or -3, x is greater than -3 and less than 5, right? Like those are examples of using inequality notation. And that's probably an Algebra 1 where you would have started, right? Like you would have been presented with an inequality and then having to like shade on the number line what values that inequality represents to make the connection between the number line and the inequality. Set notation kind of uses inequality notation in it, but it makes it look fancier. It also allows you to define like what the variable is an element of. Like, for example, for today, we're just going to be in the real numbers. So like you could say x is an element of the real numbers. Have we seen that notation before? Such that is this vertical line, blah, 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 blah. Close curly bracket. So for example, if I wanted to represent the solution set or the inequality x is less than or equal to 2 in set notation, I would say curly bracket. X is an element of the real numbers, which x could be an element of the integers or a natural number. But we're talking real numbers, so any real number. And that vertical line again means such that, and then I just state the inequality. So I would say x is less than or equal to 2. And then interval notation, referencing our inequality notation, right, where we have like the strictly less than, strictly greater than, strictly less than or equal to, or sorry, less than or equal to, or greater than or equal to. We use either parentheses or brackets, right? So you might have parentheses to represent an open interval, meaning the endpoints would not be included in the interval. Brackets to represent a closed interval, meaning the endpoints would be included. Or you can have like a half open or half closed interval, depending on your mindset. So for example, if we were representing x is less than or equal to 2 in interval notation, if we're thinking about the real number line, right, and reading the real number line from left to right, probably been drawn on here. So if we're thinking about the real number line and thinking about reading the real number line from left to right, like if 0's here and then 2, we're saying that 2 is included, and then all the values that are less than 2. So if we are reading that number line from left to right, all the values that would make that a true statement would be from negative infinity all the way up to 2, including 2. Whenever we're using negative infinity or infinity as an endpoint of an interval, it's not a finite number, right? So it's not really an endpoint, but we're describing the endpoint of the interval as being like all the negative values, all the negative real numbers, all the way up to positive 2. And in this case, when we say x is less than or equal to 2, if we were to plug 2 into that inequality, we would have a true statement, right? 2 is less than or equal to 2. So that means that we can include 2 in the interval in interval notation by using a bracket. Questions? And this is kind of a very brief overview before we get into actually like solving inequalities, just to kind of go over how you should be representing your solution sets. So because the solutions to inequalities are sets of real numbers, it might be helpful to review intersections and unions of sets. When we are talking about the union of two sets of numbers, meaning like two intervals, the union of two intervals of numbers, okay, that means that a value would belong to the set if it belonged to one interval or the other interval. So a number would be part of like a solution set if it belonged to one interval or the other interval. So in other words, I can say the union of sets A and B, so A union B, can be an element belonging to set A or set B. Union, so union, that big U, means or. And for example, if we're thinking about x less than negative 2 or x greater than or equal to 5, like thinking about that on a number line, that solution set on a number line, right? You would have negative 2, let's say that this is 0, let's say 5's over here. Negative 2 would not be included, and we would be shading values to the left. 5 would be included, and then values to the right. Or some teachers even, I know, will use like parentheses on their number line, like in Algebra 1. They were thinking ahead. They were like, I'm thinking interval notation. They would have you, instead of using like the filled in circle, they would be like bracket, parentheses, to kind of already plant the seed there. I do like the open and closed circles because I think like whenever we do get into graphing functions, and like for example, like a piecewise function where at an endpoint the graph might not be defined, we use an open circle. So I do think that that also just reinforces something else, or kind of plants the seed for like another topic.
So do we have to do the open and close bracket?
I'm never going to ask you to graph on the number line. I'm just kind of giving you a visual for representing this inequality, the solution set that this inequality represents. So a value would be part of this set of numbers, like this set of numbers, if the value would satisfy either this inequality or this inequality, but it doesn't have to satisfy both. In interval notation, I do think that the number line gives us like a nice reference, reading from left to right, of how we would represent that inequality in interval notation, which would be from negative infinity to negative 2. Negative 2 is not included. Instead of or, we use union. And then bracket 5 to infinity. And please make it clear if you're using a bracket or a parentheses. You guys, I'm looking at your homework submissions. Please make sure that we are like writing down the problem and we're trying to like write down our work in a legible and clear, logical steps, right? Like not just writing answers down. You should be writing, like if you're solving an equation, you should write the equation and then solve from there. Some were lovely, some area of growth, which we have all year to work on. Okay, for intersections. And intersections aren't at this point going to come up very often. Like I can think of a few times that we'll talk about the intersection of intervals when we're talking like domain. I can't really think of where else it would show up again this year. But the intersection of two intervals represents one interval, right? Like A union B represented one solution set. Like we're referencing one interval. We're kind of taking the union of those two intervals to create this new interval. Same thing with the intersection of sets A and B. Now for an element to belong to A intersects B, or the intersection of sets A and B, elements must belong to both sets A and B. So intersection translates to and. So for example, if we had like x is greater than or equal to -3 and x is less than +4, that could also be written as a compound inequality. But if we're thinking about like the number line, the representation on the number line, so like let's say -3 is over here, 0, 4 would be a little bit further. So if we're thinking about what this interval represents on the number line, or how it translates to the number line, going back up to this first statement here, if you graph each of these inequalities, then we end up looking for the intersection of those two intervals, like where those two intervals overlap. So, for example, x greater than or equal to -3. Oops, that's not what I meant to do. Would look like so on a number line. And then x less than 4 would be open circle at 4, but then we'd be shading to the left. So then when we're thinking about where the intersection would be, right, it ends up being from -3, including -3, up to 4, not including 4, which is how you can also think about getting from here to here. And then thinking about the number line or thinking about that inequality notation and translating to interval notation, -3 would be included up to 4. And again, you're thinking about where the two intervals that we started with would overlap. Where would they intersect? Because a value to be part of the solution set would have to satisfy each of these inequalities. Like if you substitute in 7. 7 would satisfy this inequality, right? Because 7 is greater than or equal to -3, but 7 is not less than 4. So 7 would not actually be part of this solution set. Questions? I feel like this is something that you, like when I've taught, my experience in teaching like the pre-calc honors course for a long time is that like students still have trouble understanding like intersection versus unions, and it's kind of something that takes a while to process. Are we feeling okay about this? Okay, cool. Okie dokie, why don't we get into some polynomial inequalities? I'm kind of skipping over linear inequalities, and linear inequalities would be considered polynomial inequalities, right? Because like a line, a first degree polynomial equation would be a polynomial. So first degree polynomial inequality would also be a polynomial inequality, okay? However, for the higher degree polynomial inequalities, you can't use the same strategies that were used for linear inequalities. And I do think that this is a big thing that will come up over and over and over and over again this year. And like making sure you understand coming up with a solution set for a polynomial inequality is super useful. Okay, like when we're in our discussions about domain or, I mean, that's the next place that would come up. So again, we can't simply, unlike linear inequalities, for the higher degree polynomial inequalities, we can't just think about putting x on one side of the inequality and being done. In order to determine the solution set to a higher degree polynomial inequality, we must perform an analysis to get a better picture of what values or intervals of real numbers will be part of a solution set. So like what values would make the inequality true. So in order to do this, in order to come up with the solution set to a higher degree polynomial, so second degree polynomial inequality or above, we're going to kind of focus on like the second degree quadratic inequalities. We might do like a cubic. You do want to get 0 on one side of the inequality, which is very familiar to us based on like our experience with solving equations, right? And then we want to think about, well, what does this represent? So we want all the values of x, that if we plug those values in, we would get a negative value. So we want to determine, in order to figure out like how to narrow down like what the solution sets are, trash day in Los Altos Hills. Fridays. So in order to kind of narrow down the endpoints of the intervals that could be part of the solution set, we want to think about where there would potentially be a sign change. And for a polynomial, like if we think back to even lines, but like quadratics, right? The graph of a quadratic is referred to as a parabola, right? The U shape that opens up or down. If there's going to be a sign change, the sign change would occur at an x-intercept, right? Which corresponds to the zero of the polynomial, or the x value that would make the y value equal to 0. Okay, I don't know if you guys are following this or not. But in order to give us an idea of what the endpoints of the intervals would be that would represent this solution set, we want to think about, well, where is there potentially a sign change? So to do that, we would fall back on the same strategies that you used previously in order to find zeros of a quadratic equation, which the most efficient method would be to factor. Okay, so if we were to factor the left-hand side here, of this inequality, oops, we have to have x and x, and we're thinking of factors of -2, so what is that, +2 minus 1? Okay. So the values that would make the left-hand side equal to 0 here would be x equals to -2 and +1, right? So what we're going to do is we're going to create an analysis line, and this sort of analysis, like setting up this analysis line and doing this analysis where we're looking for a sign change, is a strategy that you'll use for identifying characteristics of functions in the future. So like we're kind of introducing this strategy now for when we're looking for a sign change. So we're thinking of this analysis line as being like a real number line. So we'll put those values, oops, on our real number line in order. So like -2 and 1. And now we want to see what the sign SIGN of this quadratic would be to the left and the right of each of those values. These values, like if we were thinking about the graph of y equals to x plus 2 times x minus 1, would correspond to x-intercepts. You guys we haven't done it in this class, but I think you guys are pretty familiar with quadratics at this point. Like if you were looking at this as like, and thinking about like y equals to x squared plus x minus 2, you would, I believe, be able to tell me, oh, hey, that's a parabola that opens which direction? Up, right? How do you know it opens up?
Because the coefficient is.
I'm sorry, I looked at you and I pointed at you. That was my bad. Laura, can you help me out with this? Because the leading coefficient is positive. So it would be the U shape that would open up, right? So one kind of shortcut is like using that knowledge is that, hey, the graph would go from being above the x-axis, right? Positive, and then below, and then back above. The other method at this point, because we technically haven't talked about the graphs of quadratic functions, and so like this other way of thinking is totally fine, but to think about using like a test value. Like if you used -3, so you pick a value that's on the interval, like to the left of -2, a value that's between -2 and 1, so like 0, and a value to the right of 1. And then you think about plugging in to either x squared plus x minus 2 or the factored version is fine. So like if you plug in -3, well, that's going to be a negative times a negative, which would be a positive. If we plug in 0, we would have a positive times a negative, which is a negative. Or if we plug in 2, we would have a positive times a positive, which is a positive number. Okay? We're not done though, because now we have to interpret this analysis line. So looking at this, we're like, okay, so what interval or intervals would be part of the solution set based on looking at this analysis line? We want the values of x that would make this quadratic less than 0. So it would make this quadratic negative, which would correspond to, Zoe, do you want to say this one? So what values of x, which interval on this analysis line would make the quadratic negative? Well, 0 was the test value we used on that interval, but notice that that's on the interval from -2 to 1. So that means that the solution set here in interval notation would be between -2 and 1. Would we include, like if we substitute -2 in, would we get a true statement? No, because 0 is not strictly less than 0. So we wouldn't want to include -2. And for the same reason, we wouldn't want to include 1. Did we follow that? No, we didn't? Okay.
I'll be fine. I'll get it eventually. It's anything that makes the equation true, right? So that
The inequality true. Yes.
Sorry, the inequality.
Right, so like, okay, so maybe this will help out then. So like, let's say we were like, if we choose -3 to plug in, so if we choose -3, what do we end up with? So we get -1 times -4, right? Which would be +4. Mental math is hard right now. +4. Is +4 less than 0? No. So this interval wouldn't make sense.
Okay, so only the 0 works.
So exactly. So choosing, and you could choose any number that's on this interval as like your test value to plug in, and that test value is just telling you, like we knew that the sign change for x squared plus x minus 2 happens at -2 and 1, because those are the values that would make that 0. It has to pass through 0 for there to be a sign change, right? So that's why we can just choose one test value, and it's wherever we would end up, whatever intervals would end up giving us like a true statement is our solution set. Are you okay with that? Let's do another one. These ones are tricky. These like, this is like something I always would review in pre-calc honors, because like definitely always struggled with that. Okay. And if we were using set builder, I'm just going to go back up to this one for a second. Like if you were using set notation, which would include the inequality notation, you could say like x is a real number such that, and you could use like the inequality, so you could say like x is greater than -2 and x is less than 1, or you could even use, I think, the compound inequality for set notation if you wanted to. Okay. Next one. So, first order of business. We need 0 on one side of the inequality. So, why don't we just think about subtracting by 6 on each side of this inequality. And then we want to factor so that we can see what values would make the left-hand side 0. Because remember, those are the potential points where there would be a sign change. So thinking about what this factors to, what is that? X minus 3 minus, oh no, x minus 6 plus 1, x plus 1. Okay, so then on the analysis line, I'm going to put -1 and +6. Are we more comfortable just doing the test values, like not thinking about the graph? I think that was maybe like too much. Okay. So we can just think test value. So if I choose a value to the left of -1, like -2, pick a value between -1 and 6. How about 0 and 7? So if we plug in -2, that'll be a negative times a negative, right? Which would be positive. If we plug in 0 for x, we would get a negative times a positive, which is a negative. Like, I don't actually care what the value is, right? Like, I just care what the sign would be. And then we'd have positive times a positive when we plug in 7, which is a positive. For this inequality, we want the values of x that would make the quadratic negative or 0. Which would be between -1 and 6. So our solution to the inequality, our solution set, would be from -1 to 6. If we plug in -1, does that give us a true statement? It does. So we would want to include -1. And then what about if we plug in 6? Yeah, because 0 is less than or equal to 0. So we can plug in 6. And there we go. So the interval from -1 to 6 would be the solution set to this inequality, meaning if you choose any real number on this interval, this would be a true statement.
Would it not be negative lead you to -1 and then -1 to 6? Because
If you plug in, so if you choose a value on the interval from -infinity to -1, so for example, -2, would that create a true statement?
oh, I see. Okay.
Right? If we plug in -2, that would be -8 times -1, which would be +8, and +8 isn't less than or equal to 0. Okay, ones like this always trip people up. Everyone always is like, oh, I'm going to divide by x. No, don't do that. You can't divide by an unknown and have it cancel. Not allowed. Illegal. But we can think same strategy that we just used. Let's first get 0 on one side of the inequality. We can factor out the GCF of x so that we can see the values that would make that quadratic 0. We put those values on the analysis line in order. And then choosing test values, so like if we use -1, 1, and 5. So if we plug -1 in, that ends up being a negative times a negative, which is a positive. If we plug in +1, that's a positive times a negative, which is a negative. And if we plug in +5, that's positive times positive, which would be a positive. Now this one, remember, we want the values that would give us a true statement. So we're looking for the values, the intervals, that would make the quadratic positive. That would be over here and over here. So remember, we're thinking about my real number, or my analysis line as being like the real number line. So if I'm reading the real number line from left to right, that would be -infinity up to 0. Would we want to include 0? No. So -infinity up to 0. -infinity always has a parentheses next to it. 0 would not be included, so we put parentheses. Then we're jumping over the interval from 0 to 4 because it's not included in the solution set. I always think of it as jumping over, and the union to me, like, visually makes sense for that. Like, we're jumping over that interval. And then from 4, using parentheses, because 4 would not give us a true statement. 4 is not included. But up to positive infinity. And parentheses is always next to the infinity. Questions? Okay, let's do one more, and I want to stop at the polynomial inequalities. I'm going to put your homework up so you guys can start that, because I think doing rational inequalities is maybe, I think we need a little time for practice with the polynomial inequalities. So this is a little bit higher degree polynomial inequality, but familiar strategies. So we already have 0 on one side of the inequality. Yeah.
Sorry, so on the test, will it be covered up to this?
Your quiz?
Yeah, sorry, the quiz.
No, the quiz will just be through 0.3, so only equations.
Oh, sorry, I thought it was 0.4. Okay.
Yeah, so we're in 0.4 now, so the quiz will just be equations. Okay. Okay, so looking at this, we can't factor with guess and check yet, but we notice that there is a common factor of x that we can factor out. Okay, and then factoring that quadratic, -3 plus 2. So then on the analysis line, making sure we're putting all the values that would make the polynomial 0 in order, we'd have -2, 0, 3. Okay, choose your test values on each of those intervals. And then you can think about plugging them in. So we have, and sometimes, and this will be something that I do with the rational inequalities, but when I think about plugging into the factored version and I put the sign and I'm like, oh, so that would be a negative times a negative times a negative, which would be a negative. And for -1, when we plug that in, that would be a negative times a positive, which would be a positive. Plugging 1 in, that's plus times negative times plus, which would be a negative. Are we following this okay? And then plugging 4 in, plus times plus times plus, which would be positive. So for intervals that would make that polynomial positive, looks like from -2 to 0 and from 3 to infinity. So -2 to 0, would we include -2 and 0? Yes, right? Because 0 is greater than or equal to 0. So we would say -2 to 0, use brackets, union, because we are excluding the interval from 0 to 3, and then from 3, including 3 to infinity. Questions? So you're going to have some problems from 0.3 and then some problems just solving the polynomial inequalities from 0.4. Give me a second to get that